As we continue to work with quadratic functions, we're going to focus on using the standard form, y equals ax squared plus bx plus c. We're going to work on that standard form to start graphing quadratic functions and the things that we can do with that, because we're going to look at different forms of the quadratic function, and each one of them has their own benefit. So in standard form, we can find the axis of symmetry using this formula right here. But I think before we start talking about that formula, let's think about the things that we have learned about a quadratic function. Well, we know that they're shaped like a parabola. The parabola is the shape; it's sort of U-shaped. We know that they can open upward or they can open downward, and we know that when they open upward, they come down to this lowest point right here, which is called a minimum value, and then back up. Or when they open downward, they come to a maximum value and then continue on back downward. And we know that that point is called the vertex. And the vertex is an ordered pair. Some x and y value is going to be my vertex, and then we know that the domain of all quadratic functions should be all real numbers, because it goes on forever to my right and left. And then we know that the range is going to be dependent on my vertex. For example, here, if my vertex is a minimum, then my range is going to be some value of y that is greater than or equal to that minimum y value. Or if we have a maximum, it's going to be less than or equal to that. So again, we've worked with this, we'll continue to work with it. But what we haven't really talked about, or what we want to talk about today, is adding in the axis of symmetry, because that is going to be the imaginary line that splits the parabola, the quadratic function, in half and forms its mirror image on its right and left side. So it's a mirror image of itself at the axis of symmetry. And if you notice, this axis of symmetry ran right through the vertex. So looking at this, as we have sort of focused on those few characteristics, let's come over here and talk about, again, the axis of symmetry using standard form can be found with the formula x equals negative b over 2a. So again, the b comes from my standard form, and the a comes from my standard form, and it says x, it reads x equals. That means the line of symmetry is a line of whatever that x equals some number. And we know that would create a vertical line when x equals versus y equals is going to be some form of horizontal line. Okay, so here we know that my axis of symmetry can be found by finding negative b over 2a, and we know where the a and the b come from in our standard form. So I've been given a function, y equals negative 6x plus 4, and a is 1, b is going to be negative 6, and c is going to be 4. So I go ahead and just plug that into my formula. I have negative b, which was negative 6 over 2 times 1, which is a, and that equals 6 over 2, which equals 3. So my axis of symmetry is going to be at x equals 3. So my axis of symmetry is going to run right through x equals 3. And then let's see, what else do I know? Well, I can find my vertex. I know that the x value of my vertex is going to be whatever my axis of symmetry is, because it runs right through that x value. That's why we get 3. But remember, in order to find the output, in order to find the y value, we would want to take and put 3 in for x, and wherever there's an x, we replace it with 3, and then we can get our output. So when I take my original equation over here and I replace x with 3, then I end up with 3 squared minus 6 times 3 plus 4, which turns out to be negative 5. So my vertex is going to fall on the point 3, -5, which is right here. So I was able to find those 2 points, and let's see, what else can I graph? Some of the things that I know that, well, when x equals 0, what does y equal? And that is simply looking at this last value over here. That's going to be my y-intercept, because if I have y equals 0 squared minus 6 times 0 plus 4, when my output, right, sorry, let me do that, f of 0 is going to equal 0 plus 0 plus 4, or f of 0 equals 4, which means when x is 0, y is 4. So I know also then that I'm going to have a y-intercept right there. And we've already covered my vertex, and plug in a number between 0 and 3 to help me out. So here, right here, okay, so right there, if I pick one of those values, I'm going to go with 2. Why not? So when f of 2, and I put it back into my original function, I get 2 squared minus 6 times 2 plus 4, and that's going to equal 4 minus 12 plus 4, which is going to be -4. So my ordered pair there is going to be 2, -4. So I can plug that in. I'm going to have 2, -4. And remember that line of symmetry, everything's going to appear on the other side, so I can create these points right there. And again, because I am 3 points away from the line of symmetry, 3 points away from the line of symmetry, 1 away from the line of symmetry, 1 away from the line of symmetry. And let me see here, what can I do? I can go ahead and graph those points using a smooth curved line. And there we have it. There's my parabola. It opens upward. I've graphed those 1, 2, 3, 4, 5 points. I knew what my vertex was, which was, I knew what my axis of symmetry was. It was x equals 3. My vertex turned out to be 3, comma, -5. And there you have it. We were able to graph it. Okay, so what does the graph of this function look like? Well, I can do the same thing here. I do know that we did talk about some characteristics, that if it's negative, a is negative, then it is going to open downward. And I know that this is going to be my y-intercept. So I know that I'm going to have a point right here. And let's see, let's do a table real quick. Okay, before I start plugging in points for my quadratic equation, without using a calculator, what I can do is plug in values for my axis of symmetry. So I have x equals -b, so I have -b, which b is 4, right? Over 2 times a, and a is -1, so therefore I have -4 over -2, or 2. So it looks like my axis of symmetry should fall at x equals 2. So there's my imaginary line of symmetry. And what I can do now is I can take a couple of points on either side. Gosh, I hope that I'm going to have an ordered pair right there. But anyway, not getting ahead of myself, if I take and I have f of 2, and I plug that back into the function, I'm going to get, of course, I'm plugging 2 back in where there's an x, and then I get -4 plus 8 minus 2, which is going to be just 2. So f of 2 is 2. And there we go, we have some points. And as I've come up with here, it looks like -1, when x is -1, y is -7. So that could be down there somewhere. And when x is 2, y is 2. Of course, when x is 1, y is 1. Got some points of symmetry that I'm just plugging in. And there you go. We go ahead and connect that with a smooth curve. And again, there we have it. We have a quadratic function opening downward. Its vertex occurs right there at 2, 2. And it has a maximum value because as it runs, it starts here and goes up to a maximum value and then comes back down. And let's see, I'm not sure. My axis of symmetry, again, is going to be x equals 2. And that's about all the big characteristics that I was able to come up with. Again, I would say the first step might be finding your axis of symmetry and then determining which points you want to use right or left of it to graph. And then let's talk about the vertical motion model. And we talked about gravity yesterday and its impact. So here we have some modeling gravity. And then I have a feeling this other thing might be talking about motion, but during halftime in a basketball game, a slingshot launches t-shirts into the crowd. And the t-shirt is launched with an initial upward velocity of 64 feet per second and is caught 35 feet above court. How long will it take that t-shirt to reach its maximum height, and how far above court level will it be, and what is the range of the function that models the height of the t-shirt over time? A lot of stuff going on right there. Okay, so some of the things that we know when we're dealing with this problem is we have v, and v is going to stand for my velocity, and we said that my velocity right here is equal to 64 feet per second. And what else? Okay, did a quick drawing here. This little guy shooting the gun, and I guess we have to think about my starting point. We know the velocity, but we don't know the starting point. So let's just go ahead and call the starting point 5 feet. So then c is going to be equal to 5. And now as I put the equation together, I have my height is equal to negative 16t squared plus 64t plus 5. And there we go. I've created an equation, and let's see, how long will it take the t-shirt to reach its maximum height? Well, what is the maximum height? And we can make that determination by finding the axis of symmetry. You know, that's going to give us a good indication of that, and that is going to be x equals to negative b over 2a, and b is going to be 64. So I have negative times 64 over 2 times negative 16, negative 64 over negative 32, and that is going to give me a 2. So, gosh, it looks like 2 seconds might be the axis of symmetry. So x equals 2, and that's going to be the point where it climbs and then falls. So now that we've found the 2 seconds, let's go ahead and plug in 2 seconds for t and find out what is the height at that point in time. And then I get negative 16 times 4 plus 128 plus 5. Negative 16 times 4 is going to be negative 64 plus 128 plus 5. And that's going to give me 64 plus 5, or 69. And since we're talking about height, that's going to be feet. So at 2 seconds, I have ordered pair of 2 seconds and 69 feet. That is going to be equal to my vertex, the highest point. Okay, so how long will the t-shirt take to reach its maximum height? I think we determined that it reaches its vertex at 2 seconds. That's going to be the how long it takes to get to the maximum height. And it says, how far above court level will it be? How far above court level will it be? And then what is the range of the function models the height? Gosh, how far above court level will it be? Maybe they're talking about here. Yeah, we're not going to worry about that portion of the question. As long as we're able to model these other things, it seems like that left it a little bit ambiguous. Or if I look at that again, it says, how long will it take the t-shirt to hit maximum height? It's at 2 seconds, and then how far above the court will it be? Well, it'll be 69 feet. So that's what they were asking me there. And then what is the range of the function? Well, if I'm just going to graph it real quick, got this, got 1, 2 seconds, 1 second. We start off at 5 feet, 10, 20, 30, 40, 50, keep going up, 60, 70, and at 2 seconds we know that it is going to be at 69 feet. At 5 feet, we know it's going to be doing this, right? Coming down to 5 feet where we shoot it from. And then at 4 seconds, remember we're talking about a symmetry, it's going to be at 5 seconds again. So what is a good range and domain? Well, my domain is going to fall from here to here. So does it ask me for what is a good range? Sorry. My range. Well, what is the highest value that I reach in my height? So my height is going to be less than or equal to 69 feet. That's the highest we said it goes. And then the lowest it said it goes, well, what will the range in the over time? Well, the lowest it's going to go is probably going to be 5 feet where I shoot it from. That initial shooting spot is going to be the other end of my range. So there you have it. We've come across and we've done all the little things, looked at that basketball, the slingshot launch, and how it is working. And there we go. We're going to work on the rest of this now that we've talked about motion, and we've talked about gravity, we've covered these characteristics. And let's see, snapshot. Y equals a times x minus h squared plus k. And k, we talked about, is what makes a function go up and down. A is what makes it to stretch or compress. We're going to find quickly that this h is what moves it from left and right. And then if we have a, if a is negative, then it's going to reflect. It's going to reflect over the x-axis. So that's why if we look at this equation where it is negative 16, that makes it this shape right here. Instead of going upward, it opens downward because we reflect it over the axis. And that is a lot of the characteristics of the quadratic function. And we're going to work on doing some graphing using that axis of symmetry and moving forward with this to make it easy to graph.